Hello everyone, my name is Karthikeya Mishra and my last five digits of my roll number is 10801. So I'll begin by explaining the knapsack problem. Before that, I would like to introduce my team. We have Lakshay, Chaitanya, Tanish, Ram Kumar, Deep Kumar, and me, Karthikeya Mishra. So let's begin with the topic. So, coming to the introduction part, knapsack is a classic optimization challenge where we aim to maximize the total value of items placed into a bag where while staying within a fixed weight capacity. Each item has two properties, its weight and its value. The goal is to choose the best combination of the items that gives highest value without exceeding the weight limit. This problem is widely used in logistics, finance, scheduling, and many real-world resource allocation scenarios. The types of knapsack problems are 0 by 1 knapsack overview, fractional knapsack overview, algorithmic approaches. So coming to the 0 by 1 knapsack overview, the 0 by 1 knapsack problem involves items that can be split. Each item must be either included or excluded to maximize total value. The fractional knapsack overview problem allows items to be divided. This approach enables the selection of items fractions to optimize value within the weight limits. And the algorithmic approach uses dynamic programming for optimal solutions, while the fractional knapsack employs a greedy strategy to efficiently determine maximum value. We can understand 0 by 1 knapsack problem with a small example. I'll show you the demonstration. Suppose we have weights 60, 100, and 120. Okay. And also we have profits of these weights, which are 10, 20, and 30. So, and we have a maximum weight limit of 50 kgs. Max weight limit is 50, not kgs, because we have not been defined with the units. So max weight is 50, and the total number of items is 3. So in order to get a maximum profit, we need to arrange the weights so that we can get a maximum like weight limit of 50, but with a maximum profit. So in order to get a maximum profit, the ratio is defined by profits by weight. So when we divide profits by weight, so we get ratios like 0 by 6, 0.2, and 0.25. So selecting the minimum these ratios, with this gives the maximum profit, which is called when we add 100 and 120, which gives 220. So this is the maximum profit which we got. This was the example, the easiest example which I explained right now. And from here, my teammate will continue.
Hello everyone. My name is Ram Kumar. Last five digits of my roll number is 10769. Now I'm going to explain our code. My friend Karthikeya is explained what is the algorithm of the 0 by 1 knapsack. I'm going to explain code. Now here, the first part of our code, which is the 0 by 1 knapsack dynamic programming solution. We start by taking the capacity of knapsack along with two arrays, one for weights and another for values. When then create a DP table where each cell dp of I, dp of w represent the maximum value that can be achieved using the first I items with a weight of limit w. Inside the nested loops, we check if the item's weight is less than or equal to the current capacity. We compare two choices, taking the item or not taking the item. We store the maximum these two cases. Otherwise, if the item is too heavy, we simply carry forward the previous value. After the loop finish, the bottom right of the DP table contains optimal value of the 0 by 1 knapsack. From here, my friend Tanish will be continued.
Hello. So now I will explain the second half of the code, which is the fractional knapsack solution giving the greedy approach. First step is to compute the value to weight ratio for each item. The ratio tells us how much value we gain for every unit of weight. After that, we sort all items in descending order based on its ratio. When we start filling the knapsack by always picking the item with the highest value with the highest value to weight ratio first. If the full item fits, we include it completely. If it doesn't fit, we simply take the fraction that fits inside the remaining capacity. This strategy ensures that we always gain the maximum possible value for every unit of space we use. Once this is done, the problem displays both the final result, the dynamic programming result for the 0-1 knapsack and the greedy result for the fractional knapsack. This slide shows the output of our program for a sample input. The 0-1 knapsack using dynamic programming gives a maximum value of 220 since it's only allowed taking whole item. The fractional knapsack produces a value of 240 because it allows to take fraction of items, which increases the total profit. This clearly demonstrates the difference between the two approaches. DP gives the best exact answer when items are indivisible, while the greedy fractional method can achieve a higher value when splitting item is allowed. That's all from my side. My name is Tanisha and my roll number is 10733. From here, my friend will continue.
Hello everyone, I am Chaitanya. My roll number is 10682. Today I will explain the stack diagram shown in this slide. This diagram represents how memory is organized when our program executes the 0 by 1 knapsack and fractional knapsack algorithms. At the bottom, we have the main function. Inside main, we take the input values, the number of items, the capacity of knapsack, and two arrays, weights and values. Main then calls two functions, knapsack 0 by 1 and fractional knapsack. When a function is called, a new stack frame is created above main, and this is exactly what the diagram shows. Let's first look at the left side, which shows the stack frame of knapsack 0 by 1. Here the parameters and capacity, weights and values are passed from main. Inside the stack frame, the function also creates local variables like I and W and a two-dimensional DP table named DP. The big table in this picture represents the DP matrix. Each cell in the table shows the maximum profit possible for a certain number of items and a certain capacity. The function uses this table to apply the dynamic programming logic. After completing all the loops, the optimal result is stored in dp of n capacity, and this value is written back to main as result 1. Now on the right side we have the stack frame of fractional knapsacks. The function also receives the same parameters from main inside the stack frame. It creates local variables like max profit and most importantly ratio vector, which stores pairs of value to weight ratios and item indices. The vector is then stored in decreasing order. The algorithm picks items greedily, taking full items while capacity allows and taking a fraction of the next items when the capacity is left. The final profit is stored in result fractional, which is returned back to main. The important idea shown in the diagram is that each function call has its own memory block holding parameters, local variables, and temporary data structures. When the function finishes, the stack frame is removed and only the return values goes back to main. So overall, the stack diagram helps us understand how our knapsack programs use memory, how the functions are executed, and results flow back to the main programs.
My name is Deep Kumar. My roll number is 10783. Now I am continuing about this slide represents the 0 by 1 knapsack approach with fractional knapsack approach. 0 by 1 knapsack using dynamic programming works only for indivisible items. Always gives the exact optimal result. Uses more memory and time. Best for discrete items like project features, packages, or tasks. Fractional knapsack using greedy works when items can be split much faster and very stackable. Uses very little memory. Best for divisible materials like grains, liquids, or raw resources. So DP is best exact results and greedy is best for speed. Now my friend will continue.
All right, everyone. Let's, with that, move to the last part of our presentation. Okay, so let's start. When to choose 0 by 1 dynamic programming. We do it when items cannot be divided anymore. You need an exact optimal solution result. You go through the dynamic programming. And when the capacity and number of items are moderate, we choose 0 by 1 dynamic programming. And when do we go for fractional greedy? If you ask, when we want fast scalable solutions, we move towards to greedy method. It is approximate when we want quick and best possible results. So now let's ask ourselves, where do we use zero by one knapsack in our day-to-day life? We might not notice it, but fractional knapsack is all around us. From shipping our Amazon parcels, Flipkart parcels used in cargo shipping methods, we use zero by one knapsack. Also, in our own university, in embedded systems, we use algorithms for solving module functions using zero by one knapsack. Also, in disaster relief systems, we follow zero by one knapsack. Same goes with investments and budgeting advertisement plans. This problem is widely used. Also, in features like creating website time budget constraint and server and VM allocation, we often use zero by one knapsack. We might not notice it, but zero by knapsack handles more situation around it than we imagine. So, with that, I would like to conclude our presentation, showcasing how zero by one knapsack is important and changes things around us. Thank you. That will be all from our side. And with that, we all are done.
Excuse me. In the end, I would like to thank Sarvani and Nandara ma'am. Thank you for giving us this wonderful opportunity to express ourselves. We truly appreciate the platform you provided to share our creative ideas. Your encouragement created a supportive environment that boosted our confidence. We are really grateful to you. Thank you, ma'am.